Okay. Everyone doing okay? Class seems like it's getting smaller and smaller and smaller. We almost finished up last class, 10.7, so I want to go ahead and finish up this section. We talked about a couple of the applications for the vector functions. Specifically, we were talking about how if you have a vector function that gives you the position of an object with respect to time, that the first derivative was, we called it v of t, was the velocity vector function. The second derivative was a of t, was the acceleration vector function. And because of that, we can use integration to go backwards. Starting with acceleration, we can go back to velocity, and then from velocity go back to position. So this is the kind of note that explains that. And then I got to this example and I didn't cover it, right? So this is what I'd like to do. What we have is we are given an acceleration function. We are also given what are called initial conditions. So I'm going to write down here, I'm given that the acceleration vector function for this particular object is t e to the t e to the negative t. I'm also given that, bless you, r of 0 is the vector 0, 1, 1, and v of 0 is the vector 0, 0, 1. Now, this is all my given information. I know the acceleration of the object at every moment in time. I know the position of the object, right? R of 0 is the position. R is the position function. R of 0 is the position vector at time 0. So I know where this thing was at one point in time. And I also know the velocity of this thing at one point in time. So I don't know if you remember from Cal 2, these were called initial conditions. This is what was happening at the very beginning, right? At time 0, this is where it was and how fast it was going, velocity-wise. So let's start by trying to recover the velocity function. Oh yeah, and we're asked to find r of t. Sorry, we're asked to find the general position of this object. So to start out, what I'll do is I'll find v of t. V of t is the antiderivative of the acceleration vector function with respect to time. And so we saw that when you integrate a vector function, you integrate each component. So all I have to do is integrate each of these components the way I did in integration in Cal 2. So what's the antiderivative of t? With respect to t, it's 1/2 t squared plus a constant, right? But watch how I'm going to do this. Then e of t, right? Antiderivative of e to the t is, I said e of t, e to the t is itself, right? Plus a constant, which I'll take care of in a second. And then the antiderivative of e to the negative t is negative e to the negative t. So we have to worry a little bit about chain rule. And then I'm going to say plus some constant, right? But that constant is not a number. The constant is a vector. Because each of these individual component functions had a constant to them, didn't they? So if I put those constants together in a vector, that's going to be this c. Pardon me? Yeah, it's 3 numbers. I'm not quite sure what they are at this particular moment in time, but I'll find it in just a second. So we have this. Now I'll actually write that c vector out as c1, c2, c3. Okay, so this c vector is some vector that has 3 components to it. So I know my velocity function within a vector constant. I know that much about it. So now I'm going to go and try and figure out what that vector constant is. So I need to use one of the conditions that were given. So we say, but v of 0 must equal the vector 0, 0, 1, which implies that when I plug in 0, right, here, here, and here, and I add my constant, I should get this vector, right? So that means that when I do 1/2 times 0 squared, e to the 0, negative e to the negative 0, still 0, plus my constant vector, that I should get 0, 0, 1. Now what is this vector when I plug in 0 here? What do I get? 0, 1, negative 1, plus my constant vector must be 0, 0, 1. And so to get this constant vector, which is what I'm trying to figure out by itself on one side of the equation, I can basically subtract this vector on both sides, right? Subtracting the vector 0, 1, negative 1. Vector subtraction, you just subtract the components, don't you? So we get that C1, C2, C3 must be the vector what? 0, right? 0 take away 0, and then 0 take away 1, negative 1. And then 1 take away negative 1, which would be 2. So now I know what my constant vector must be in order for it to satisfy that initial condition. So now let's go rewrite the vector function for v with the constant integrated into the function. So my v of t was the 1/2 t squared e to the t negative e to the negative t plus that constant vector, which I just found was negative 1, 2, right? So that's up there. Now I know what that constant is. Now put them together, right? Add the components together, and I'll do it on the next page. So what do we have? V of t is 1/2 t squared, then plus 0, so I don't put anything. And then it was e to the t, but then minus 1, and then negative e to the negative t plus 2. And that is the exact vector function that gives me the velocity for this object. Double check it real quick. If I plug in 0, I get what? 0, 0, 1. So it does match what it was supposed to. Now I'm supposed to get r of t. So I have to basically repeat the exact same process again, right? Go backwards one more time. So I'll go a little quicker this time. R of t is the integral of v of t dt, which is antiderivative here is 1/6 t cubed. Antiderivative of e to the t minus 1 is itself e to the t minus the antiderivative of 1 is t. And then the antiderivative of negative e to the negative t is e to the negative t. The antiderivative of 2 is 2t. Plus some new constant vector, which I'll call d. And then we go through and do it again. Y'all agree with that antiderivative? All right. Oh, by the way, the quizzes you turned in on Monday, I plan on grading those today. I didn't have time to get them done, so hopefully next Monday I'll have those for you. All right, so let's go ahead and start plugging things in. I'm going to try and do this, like I said, a little quicker. I knew that r of 0 had to be the vector 0, 1, 1. Which means that when I plug 0 into this, what do I get when I plug in 0 to this? 0, 1, 1 again, right? Okay, 1 again. Plus my D vector, that has to be equal to this right here, right? Doesn't it match already? Isn't that exactly it? Isn't this exactly what I want here? So what's D? D is the 0 vector, which means I don't have to add anything, which means that my position function is just what I got earlier. It's the vector function 1/6t cubed, e to the t minus t, e to the negative t plus 2t, done. Questions? On your take-home, right, your take-home quiz that I gave you from last time, there's a problem like that, I believe. Shit. Isn't there? The second one, if A of t is this nasty looking thing, I give you initial conditions and you go back and you get the vector function. Was there a question? Yeah, R of t, is that the position at any point in time? That's right. So what if I said now, what's the position of this object at t equals 2? You would just plug 2 into this, and that would be the position vector, right? And that ties into what you, on the question that you have to do for the take-home, right, the quiz, it says, here's the acceleration, here are 2 initial conditions. Find the distance from the particle. So there's a particle that's moving along a curve. You have to find that curve, representation of that curve. And then I say, how far away is that particle at t equals 1? So at t equals 1, you're at a certain place. How far is it from a plane? So you basically have a point in the plane now, and then you work that out. All right, I believe that's it for this section. I had checked last time, right, that that was the right page number? Yeah, 589. All right, so that's it for 11 or 10.7. I believe that's the right page, 589. It's 10.7 in the book, or 10.7. Let me go ahead and open up the next set of notes for 10.8. All right, some instructors here don't cover this section, but I'm going to do it because I think there's some valuable stuff in here. Arc length and curvature. All right, so if you have a curve in 2-dimensional space given by a vector function, so we have some vector function here. It has 2 components because we're in 2D. And we want to move along this curve and traverse it exactly once. That means, think about, there are ways we can draw a circle, right, with the vector function. Well, if you draw a circle with the vector function, eventually you start drawing on top of itself again. So this formula will only work if we traverse that curve one time. So don't draw on top of itself. So as long as we traverse just once, our t is then restricted between 2 constants, right? The starting time and the ending time, which we're calling a and b. If we do that, restricting our curve between 2 points, then we can find the arc length using this formula right here. It's the what? What is this? What is the magnitude of the derivative. It's like the speed, right? Geometric, I mean, in terms of a moving particle, it's like finding the speed at every point. But geometrically, what we're doing is we're taking a curve and we're trying to approximate the length between here and here. So the way we approximate it is by looking at the derivative is a tangent vector, right? And we're approximating this infinitesimally. Remember, it's like an infinitesimal length. We're approximating it with the length of the derivative. That's basically what's happening. We're adding up all the little lengths of the derivatives. And it's kind of like the right triangle thing that we did in Cal 1. All right. Yeah, like in calculus, that's exactly what we did. We let, like when we were trying to find, in Cal 2, when we were trying to find the area under a curve, what we did is we cut it into rectangles, and then we let the width of the rectangles get smaller and smaller. Or you could say we let the number of rectangles go to infinity. Same thing here. We're looking at it. We're looking at the length between 2 points on the curve, and then making it infinitesimally small. All right, so find the arc length of this vector function from 0 to 2 pi. What do you think our answer is going to be? What does r of t draw? What does this r of t draw? Unit circle, right? So radius 1. And I'm going from 0 to 2 pi, which should draw the whole thing, right? So shouldn't this just be the circumference of a circle, radius 1? What's the circumference of a circle? 2 pi r, so our answer should just be 2 pi. Well, let's see that that's what we get, all right? So I'm trying to find the arc length of r of t equals square root. No, that's not it. I'm getting ahead of myself. It was cosine t, sine t. We're on the interval t is between 0 and 2 pi. Now we have to know that that's only traversing the curve one time, right? If this was 0 to 4 pi, I couldn't use the arc length formula, correct? Because I'm drawing it twice. And then the formula actually falls, it fails. It doesn't work. You would still get 2 pi if you did it. If you did this from 0 to 4 pi, your answer would still be 2 pi. So, all right, so the formula is the length. Do I use L? Yeah. So the arc length will be the integral. Here, A for us is 0, B is 2 pi. So 0 to 2 pi of the magnitude of the derivative. Let's go do that on the side. What's the derivative of this vector function? Negative sine t, cosine t. Okay, what's the magnitude of the derivative? So what's its length? Square root of each of those squared? Each of the component functions squared? So when you square the negative sine t, you just get sine squared t. The negative doesn't matter. When you square cosine, you get cosine squared t. And how about that? That's just 1, isn't it? And then nice. So we're just going to integrate 1 dt with respect to t. The antiderivative of 1 with respect to t is just t. And we're going to evaluate this integral at 2 pi and then subtract from it what we get when we evaluate at 0. So we plug in 2 pi and we just get 2 pi. We subtract from that what we get when we plug in 0 at 0. And that just gives us 2 pi. And that makes us happy because it makes sense that it would be 2 pi, right? But this goes for all vector functions now. You can always find the length of the vector function between 2 points on the curve by using this. Let me help you with this take-home. This is a huge hint. I'm hesitant to even give you this hint. If I tell you to find the length of a curve between 2 points, you just apply that formula, don't you? Is that what I give you on the take-home? Do y'all have it with you or not? Yeah? What does it say? Read that problem out. What does it say? I don't know. Let me see. Which one is it? Where the heck did I put it? It's 3? Yeah, here we go. Number 3. If R of t represents the position of a particle at time t, so I give you a position function, right? If the particle starts at the point 0, 0, 0 and moves a distance of 4 units along the curve, then where is it now? So in that problem, I'm saying it moves a distance of 4 units, right? So if I imagine you have here, I don't have any chords in here. Oh, yeah. Let's say that this cable here represents the path of a fly in this room, okay? So it starts out here at my hand, and it flies through the same path as this, right? If I tell you that the fly started at 0, 0, right here, okay, and traveled a distance of 4 units, where is it now? Then I want to know where this is, right? What's the point right here? You understand? So I'm not giving you A and B in the problem. I'm not explicitly giving you A and B, am I? I'm giving the distance, right? So I'm saying if you straighten that out, it's 4. So I'm giving you the arc length, right? That's all I'm going to say. A lot of people, when they do that problem the first time, they think the 4 somehow has to do with one of the endpoints or something, and it's not it. I'm giving you the arc length. You have to figure out, right? Look at this. Well, go back to the formula for this. If the arc length is an integral, right? I'm giving you the arc length. I'm giving you the vector function, which means you can take its derivative and its magnitude. And then the only things that really are left to be resolved are what? A and B. Well, kind of, because I give you that it starts at 0, 0, 0, right? That's the A and the B are your values of what? T, right? So you can't plug 0, 0, 0 in for A. You know what I'm saying? You're going to have to somehow recover what A is first. Okay, I'm going way past what I wanted to do. I've basically given that away. I hope that this is kind of working for you as far as your brain is concerned, because like in class, this is a very direct problem. Here's R, here, let's find the arc length, we're done. But your take home is completely different than this, and it requires that you truly understand what it is that you're given and what it is that you're trying to find and apply the formula. This is too much like what we call monkey see, monkey do, right? Here's a formula. Now you do a problem just like that. Just do everything I did and don't care about what you're really doing. Just do it exactly the way I did it. That's not the point for me of a class like this. Okay, moving along. Oh, that's just a picture of it. All right, now if we move to R3, so 3-dimensional space, right? Everything is the same. Everything is exactly the same. We still need to traverse it only one time, the curve. We still will have a starting time and an ending time, an A and a B. The only difference is that your magnitude is a little different because the magnitude of a 3-dimensional vector has 3 pieces to it. So it'll be a little more complicated. And that's like the one on your take-home. Right, number 3, that's a 3-dimensional vector. So you're going to have to figure out what the heck all this is at home. And it cleans up, all right? It actually cleans up. It's not going to be as bad as it looks. But here's a good example that might help you with getting your mind around that take-home as far as, I gave you a point, didn't I? Like, I gave you the point start at 0, 0, 0. Look at this problem, how it's different than the one we did earlier. Earlier I said find the arc length of r of t is cosine t sine t from 0 to 2 pi. And I gave you a is 0, 2 pi is b, right? Here, I give you a starting and ending point. So let's recover what a and b are from the points. And then we'll be able to do all the work. See the difference? So if r of t is cosine t sine t, t, what does that draw? It's like a spiral, it's like a coil, like a spring, something like that. Fixed radius, right? There's your starting and ending point, right? Now it is important that we start here and end here. We don't want it to go the other way. Although the arc length shouldn't matter, should it? So let's start by trying to figure out what a and b are. In order for me to figure out what a is, I need to know what value of t I would plug in here to get me to start at this point. And is that kind of obvious? T is 0. Again, look, this last coordinate has to match up with this one right here. So t has to be 0. And then this one's almost as easy, right? Last coordinate t, pi. All right. It's subtle, but it's something we have to do in the problem to make sure we have to have these values, right? How about a derivative? We need that in the problem, and then we need its magnitude. So derivative is the vector function negative sine t cosine t1. The magnitude of this is square root of what? Sine squared t plus cosine squared t plus 1, which is just root 2. The previous problem, when we did the magnitude of the derivative, we got 1, didn't we? And this one we got root 2. Are you always going to get constants? No. I think on your take-home, you're actually going to have to integrate something other than a constant. As far as I remember, yeah. All right, so can we set up the arc length? It should be integral 0 pi of root 2 dt, which is just root 2 t, evaluated from 0 to pi. So what's the answer? Square root 2 times pi. I'll write pi root 2. I like to always write any constants I have out in front of a root so that people don't accidentally think that the pi is underneath the root. That's it. One more example. Here's the example. Oh, there's the picture of what we did. I think you understand that we're just measuring that length, right? That curve right there. We're just measuring that. It's coming out to, right, some value. How about this? Here's the curve in three-dimensional space. That's the curve that we're trying to look at. We're going from t equals 0 to 1, so we're trying to measure out that part of it right there. Just this piece. How long is that? So the vector function is r of t is 2t to the 3/2 cosine 2t sine 2t. And then it says in the problem, on 0, 1, which means what? That's my values for t, right? T is 0, t is 1. So A is 0, B is 1. So before I do arc length, how about we get derivative? The derivative of 2t to the 3 halves is 3t to the 1 half. The derivative of cosine 2t is negative 2 sine 2t. The derivative of sine 2t is 2 cosine 2t. And now I need that magnitude. Magnitude of that is the square root of each component squared. So what is 3t to the 1 half squared? 9t. And then plus, what the hell is that? 4 sine squared 2t plus 4 cosine squared 2t. That's like those little party things? Is that one? Wow. You hear people singing too? Oh. Thank you. They sound like they're having a little more fun than we are. All right, what about this? You want to integrate that? Probably not, right? You see some stuff that cleans up in here? Look at these two terms. Can I pull a 4 out of those? Just those two? I can do that, right? And then sine squared 2t plus cosine squared 2t is 1. So that's just square root of 9t plus 4? Are we ready to integrate? I might have to walk over there in a second. That okay? All right, so now let's do our arc length. Arc length will be integral from 0 to 1 of the square root of 9t plus 4 dt. How are you going to integrate that? Just a basic u sub. This is a basic u sub. I am going to go over there if that continues. That's a little rude, whoever's class that is. All right, I think you get 1/9 times 2/3 9t plus 4 to the 3 halves. Evaluated from 0 to 1. Let me just check that real quick. Derivative of this is that's gone, then you have the 1/9 derivative inside. Yeah, that should work. Okay? So I just did a basic u substitution here. U is equal to 9t plus 4, and then I worked it all out. So plug 1 in. Let's see what we get when we plug in 1. Ooh, 13. So it's going to be an ugly number, but I'm just going to leave it, ugly. 2 over 27, and then it's 13 to the 3 halves, minus, now when we plug 0 in, what do we get? 4 to the 3 halves? What is 4 to the 3 halves? 4 to the 3 halves is the same as the square root of 4 cubed, isn't it? So that's just 8, right? 4 to the 3 halves, you raise it to the third, but you take the square root. So I take the square root and then raise it to the third. So 8, this is just 8, and then times, so 16/27. That's the exact answer. You could put things together, and you could definitely get on a calculator and get a decimal, but that's it. All right. Curvature. Give me just a second. I'm going to try not to. Okay. Now, This is a very interesting topic right here. Curvature. All right, curvature. The curvature of a vector function is a number which represents how quickly a curve changes direction at a given point. And there are two formulas that we use to compute curvature. We use this K symbol here for curvature, and then here are the two definitions. Now, depending on the situation, one of these can be better to use than the other. But let's just talk about what each one of them is, all right? The first one, do you remember last class what capital T is? Capital T? Capital T is the derivative, it's the derivative of the vector function divided by its own length, right? But then you're supposed to take the derivative of that, and then take the magnitude of that. Understand? And then divide it by the length of the derivative. If you take that computation, that'll be a number. Well, it'll be a function. If you plug in a value of t, it'll be a number. And that tells you the rate at which your curve is, your function is curving, like the rate at which it's turning. The higher the number, what? You would think the sharper the turn, the smaller the number, less turn. I'll show you a picture in a second. Now, this is another formula that gives you the exact same number. And you can show that these formulas are the same by just messing with them, but I'm not going to. This is a nice one to work with because all you have to do is take a first and second derivative and then cross product those and then take its magnitude. And then divide it by the derivative, which you already would have gotten because you did it here. And then cube it. It's weird. But that's what it is, all right? The only drawback to this formula for curvature is that you've got to be in R3 to use this one because cross product's only defined in R3. Now, we can always extend ourselves from two-dimensional space to 3, but I haven't shown you how to do that yet. It's pretty easy, but I haven't shown you. So here's an example. The example below shows that the curvature of a circle is constant. Would that make sense to you? You're going around a circle. The curvature should be a constant. All right, so let's go ahead and see if we can compute or look at the picture first. You know, as I'm now the curvature is 1. So I'm having the computer compute the curvature at every one of these points as I move around, and it's just staying 1 the whole time. Compare that to the example we'll do after that, which is this one, this spiral. It starts out, it's a tight spiral, and then it kind of spreads out. So in the beginning, you're going to have very, very sharp turns, and then as you go out, the turning is not as sharp. So look at my curvature right now. My curvature is 33,331. So the program I wrote for this is actually calculating that whole thing at that particular point t is 0. And as I press play here, I might have to slow it down. Yeah. So as time goes on, right, you can see that the curvature just started to get smaller and smaller. And actually, we have a, you know, like 0.1, 0.01, 0.04, right? So it's getting smaller as I go. Do y'all see that? So you see how the curvature idea matches the picture? Questions? You have this look on your face. Well, I'd have to zoom in. You can't see in there. It actually spirals a couple of times. What do you mean, asymptote? You know what? I don't know what this function is. Let me see it. Like, is it defined at the origin? Is that what you're saying? Let me look at the curve. I don't remember what I'm drawing here. I'm drawing this right there. Whoa, crap. It's just this. So it's t cubed cosine 10t, t cubed sine 10t. So it is just a spiral. At 0, it's defined. It's just as soon as you start letting T go bigger, it starts drawing circles, right? And there's just a bunch of them in the middle you can't see in the picture. So it's spinning and then it starts to open up. Because your amplitude for these trig functions is getting bigger. Once you get past 1, right, these numbers start getting big, fast. So your amplitude starts spreading out, so your curvature is less. That makes sense. Did I answer your question at all? You're correct. This is not one example. Do you want to show that the curvature of this is constant? How would you go about that? Well, let's do it. Let's just do it real quick. If we can do it real quick. If we have R of t equals cosine t sine t, let's show that the curvature is 1, right? According to my graph, it was. So the curvature of the formula I'm going to use is capital T prime t over, what is it? R prime magnitude. So let's go get some stuff over here. To get t of t, I need to do R prime t over its own magnitude. What is the derivative? Negative sine t cosine t? What is its magnitude? It's going to be 1, right? Do I need to write that down? It'll be square root of all that stuff. It's going to be 1. So capital T is the vector negative sine t cosine t. That's not what I need in the formula, though, right? What do I need? Its derivative and then that magnitude. So the derivative of capital T is negative cosine t negative sine t. And then what's the magnitude of this? It's going to be 1. Is that okay? So the top is 1. Yay. All right, what about the bottom? Well, it was the magnitude of the derivative, right? Which I had done right here, didn't I? So it's 1 over 1. So it's 1. Constant magnitude, sorry, constant curvature. See, that formula wasn't too bad to apply, was it? Now, what if I wanted to use the other formula for this? How would I extend it into R3? So this is what you could do. Is you take the original vector function, and to extend it into R3, was it sine t? No, cosine t sine t. Is just add a third component and make it 0. That's it. That's all it takes. Because all that does is takes it in 3-dimensional space and flats it down. The z coordinates or z component's always 0. It just flattens it down to the xy plane. And now, let's see. To use the other formula, I need the derivative of this, which is negative sine t cosine t 0. And then I need the second derivative, which would be negative cosine t sine t, no, negative sine t 0 again. And in the formula, what am I supposed to do with those two? Cross product of those two, and then the magnitude. So let me do that real quick, cross product. If I take r prime and cross it with the derivative, second derivative there, then is it all right if I do the cross right here? I did it right here for a reason. We cover up the I components and we do this, right? So what do we get? 0, right? So this cross product so far is 0. And then when I do the middle one, what do I get? 0 again. And then when I do the k, I get what? Sine squared t minus negative cosine squared t, which is sine squared t plus cosine squared t, which is 1. And then the magnitude of that, no? This times this gives me positive sine squared t. And then remember, it's determinant, so now I say minus this times this. This times this is negative cosine squared t. So I subtract negative, it becomes plus. That's 1. And so now we need the magnitude of this, right? The magnitude of that would be the magnitude of that, which would just be 1, obviously, right? That's the numerator. And then we divide that by the magnitude of r prime cubed. The magnitude of r prime is 1. Cube it is 1. We get 1. So either way, we got the same answer. I'm not going to finish it. All right. How about this one? Find the curvature of this vector function. T1 plus t squared. Doesn't look very ominous, doesn't it? I mean, it looks okay. Yeah, how bad could it be? T1 plus t squared. Shall we try the first one? The first formula? Yeah. Okay, let's try it. What's capital T of t? Well, that's r prime t over its own length, which is, what's the derivative? 1, 2t. I'm not feeling too bad about things yet. Over, what's the magnitude of that? Square root of the sum of the components squared. So 1 squared plus 1 squared plus 2t squared, which is 2 plus 4t squared, isn't it? Yeah? And if I put that together all in one vector, I actually have now 1 over the square root of 2 plus 4t squared, and then 1 over the square root of 2 plus 4t squared, and then finally 2t over the square root of all that crap again, right? And what do we need to do with that? Take its derivative, and then the magnitude of that. So you, at this point, start going, maybe that other one's better, right? Do you see why? Because, I mean, I don't think anyone here wants to take the derivative of this, and then the derivative of that, and then the derivative of that, and then find its magnitude. It could be a catastrophe. Could it be done? Yeah, I'm sure it could be done. But maybe the other formula works better. So right now I would stop and go, you know, like, huh? Do I really want to do that? So for the other formula, all I really need to find right now is the second derivative, right? And then cross it with that first derivative. But I'm going to write down the first derivative so we have it so I can do the cross a little easier. 1, 2t. Ooh, look at that second derivative. 0, 0, 2. That's nice. Look at the cross product of those. What do we get? Cover up I, you get what? 2. Cover up J, you get 2. Remember, we changed the sign on the middle one, right? So negative 2. Cover up K, 0. Do y'all see that? And I just need now the magnitude of this, right? What's the magnitude of that? So the magnitude of this is the magnitude of that is the square root of 4 plus 4? 8. Damn, that was pretty clean, wasn't it? And the only thing left to do is divide that by the magnitude of the derivative cubed, right? So I'm going to come over here and write down k. K is equal to square root of 8 over, what's the magnitude of the derivative? It's this right here, right? That's your derivative. Magnitude of that was what? And we did that earlier, didn't we? So, but then take that and cube it. Agreed? We're done. That's the curvature. I don't have to go cube that or anything. Just leave it. But by looking at this, is the curvature of this particular vector function constant? No. What happens to the curvature as t gets larger? It gets smaller, right? You could say as t goes to infinity, the curvature approaches 0. Yeah, if t is in there, then somehow the curvature depends on t. Yeah. Okay, so that was to illustrate the difference in the two formulas. The first example I did where we calculated curvature, it was pretty easy to use the first formula. Second formula wasn't bad either with that first example. This example, first formula, I wouldn't even mess with it. And then the second one worked out great. All right, that's it. Chapter 10 is done. That's the wrong page. Can someone tell me what the page number is for 10.8 homework? I think there's not one in here. 592? Thank you. Yeah, I'm sure there's one in the hallway or... You should go into the classroom across the way where they're making all that noise and just go sharpen your pencil. Thank you, excuse me. Is it 592 or 598? All right, so we're done with chapter 12. I mean, 12. Chapter 10. So we enter into the next chapter, chapter 11. Remember, our goal here is to finish the book, so we're supposed to finish chapter 10, 11, 12, and 13. Chapter 11. Can someone tell me what the chapter is called? I believe it's called. No, I'm not gonna act like I remember it. Chapter 11. Look at the very beginning of the chapter. Right there, right there. Multiple. No. What is it? Partial derivatives. The chapter is called partial derivatives. All right. I didn't remember that. I thought it was going to be multiple. No, that's chapter 12. Never mind. I'm confusing them. Partial derivatives. All right. What we're going to do right now is we're going to take a step, not backwards, but more like sideways. Like in Calculus 1, everything we did in Cal 1, we dealt with functions, right? F of x equals something. So you looked at an input and an output, right? Input, output. What we've been doing right now is we kind of stepped away. We started talking about three-dimensional space. We started talking about like surfaces, planes, lines, vector equations of curves. And now we're going to start to look at just the traditional scalar functions like we did in calculus, f of x. But we're going to extend it now to several variables instead of just one variable. So we have seen so far that when we have an equation that has x, y, and z in it, we get surfaces. Okay, so when we have an equation, those three variables appear, we get a surface. Examples, cones, paraboloids, spheres. But all of those were just equations, right? There was no like f of x. It was just an equation with x, y, z in it. All right, now what we want to do is we want to look at if it is possible with an equation, if it's possible to isolate the z variable, get it by itself on one side of the equation, just z, then z can be determined if you know what x and y is. Right? You isolate the z, someone gives you an x and a y, you can tell me what z is. Therefore, z can be looked at as a function of the two variables x and y. Yes? Note also that to be a function, there still needs to be one input, one output. So I'm going to step away from this just for a second, give you something here. X squared plus y squared plus z squared equals 1. What does that draw? Unit sphere, sphere radius 1, centered at the origin, right? Can you solve this for z? Move everything over to one side, right? That's a minus. But I don't have z by itself yet, right? I need to do square root. And whenever you do square root, you must include plus or minus, don't you? Plus or minus? Can this be written where z is some function of x and y? One input has to be one output. So if I plug in something for x and y right now, right, an x and a y, that's considered one input. Am I getting one output? No, I'm getting two because I have a plus and a minus, right? This would not be a function. And it kind of makes sense if you look at it. Here's your sphere. If the ground is x and y, if I plug in a particular x and a particular y value, that's some point sitting on the xy plane, isn't it, on the ground? If you try and take that point and plug it into the function, it has to draw the top of the sphere and the bottom of the sphere. So that it's kind of like it goes up and gives you some point up here, but then it goes down and gives you some point down there. Does that kind of make sense? So one input, two outputs. So it fails. I'll get into that more here as I keep going. Also notice the notation, right? F of x, y. Everything we've ever done, it's only been x, right? Now you're saying that f, the function, depends on two things instead of one. A function of two variables. With this notation, it's important to see that the domain of the function, the inputs, are ordered pairs. Cal 1, your input was always just a number, wasn't it? A single number. Now, the thing that you plug into the function is a point, an x and a y coordinate, an ordered pair. This means that the domain of the function is two-dimensional, right? Yes? You need two dimensions to represent what goes in, and you need one dimension to represent what comes out, because your z value spits out a number. So two dimensions for what goes in, one dimension for what comes out, which means we need three dimensions to visualize this. It's kind of like this. Back in the very beginning of things, when you were dealing with a function like f of x equals x squared in Cal 1, we all know that that looks like this, right? Maybe what we didn't realize when we were doing that was that we were just trying to find a way to visualize the function. So we had the x-axis and y-axis. This was our input, right? And this was our output. Yes? Input and output. Another way to look at it is your input and your output. What you did is you took in a number, right? Some number. We called it x. And it was a number. It goes through the function, gets squared, and comes out as another number. So it comes out over here. Like, for example, if this was 2, this would come out over here as 4, wouldn't it? But this output is a number. But imagine me trying to draw a picture that shows all these connections. That picture would suck, wouldn't it? Compared to this, where you have it all together, inputs, outputs together, you can see that if I plug in 2 here for x, you get out the 4 up here on the y. Yes? So for the functions that we're dealing with right now, these functions where we have x and y going in, to visualize it, I would need my input to come from two-dimensional space, my output to be a number. So I must pick my input first, which I can represent as a point in two-dimensional space, and then throw that point down to some value, right, some number. Total number of dimensions needed to visualize is 3. Now, where are we going to run into a problem? What if we have a function where we want to have 3 inputs and then have it spit out an output? Yeah, you won't be able to visualize it, right? Because if I had a function, like right now, this is the point x, y. It goes through and it spits out some z value, right? Which is some function of x and y. If I had something more complicated, where I wanted to give you an x, y, and a z, then your input would have to come from three-dimensional space, some point sitting here, go out some x, go out some y, go up some z, pick that point and drop it off on a number line, right? You need a total of 4 dimensions to be able to visualize that, and you won't be able to do it, right? We live in three-dimensional space. 4 dimensions is kind of tough to understand, right? What about these computer algorithms that weather forecasters use, where they go to their computer and the computer is reading the temperature outside, wind speed, barometric pressure, humidity, right? All these inputs, and then it runs it through some function and spits out probability of precipitation, right? The function input is maybe 20-dimensional, 20 inputs, and spits out 1 output. There's no way to visualize it. But all of the calculus that we do behaves the same in all those dimensions. So what we're going to do is we're going to start now to move into functions where you have 2 inputs. What does the calculus look like here? And then we extend it. What if the function has 3 inputs? And then if you go higher in math, then you just go to n-dimensional space. And it doesn't matter anymore. We don't even care about the visualization. All right, does that kind of make sense what we're doing? Now, we like functions like this because they are 3-dimensional, and so many things in our world are 3-dimensional, right? We live in 3D, so we like it. What do a lot of people say 4th dimension is? Time, right? Like I'm here. This computer's been sitting here, right? The computer is not moving. Physically, it's in the same position. Well, if relative to the Earth, right? Relative to the sun, it's not. It is moving, but let's not get into that, right? So this is not moving. It's static relative to this room. And so, but it wasn't here 2 hours ago. So if you look at, what happened, where was this at t equals 0, which maybe was the beginning when I showed up to work, it's at a different position. But now at t equals whatever, 2.5 hours, it's here. So you can look at that 4th dimension as time. Does that make sense? Speaking of relativity, I can never stay on topic. I'm sorry. It's just one of those days. Theory of relativity. Einstein's theory of relativity, right? Everything's relative. You've heard terminology like that. I'm going to give you one of the best examples that I ever was given to explain relativity. Let's say that you have a person that holds a ball 6 feet off the ground, okay? Drops the ball, starts calculating the time. The ball drops, bounces back up. Let's say the ball bounces back up to here. And let's just say the total distance it traveled was the 6 feet it took to fall. And let's say it bounced up 2 feet, all right? So if it went down 6 feet and bounced back up 2 feet, and that's where they stopped the clock, how many feet did it travel? Total. 8 feet, right? 8 feet. Let's just say, for the sake of making this easy, that when they timed it, it took exactly 1 second for that to happen. So would you agree that if that were the case, the ball had a speed of 8 feet per second? Yes? Okay. Now, what I didn't tell you is that the person that was actually doing this experiment was in a car, or in the back of, let's say, a truck. All right? So when now from a person that was standing on the street, and the truck is moving, okay? The truck is moving. Let's say the truck has a glass side to it. So the person looking from the outside sees the person come by and drop the ball. But what does the path of the ball look like to the person who's on the outside? The ball starts here. As it's dropped, since the truck is moving, it appears to do this, right? And then come back up like this. Imagine the truck is moving, so the ball has to move with the truck, right? So it's going to look like that to the observer. Well, we know that this length right here is 6, and if this is going to be like a right triangle, the hypotenuse has to be greater than 6. And then if this right here is 2, how high it came back up, then this hypotenuse right there is greater than 2. So it actually went, yes? Well, hold on, let me finish. So this is a longer distance and a longer distance over the same period of time. So relative to the observer, the ball had a different speed. Yes? What's that? What do you mean? Well, it's like this. I don't have a ball, but you know, y'all are the observer, okay? Here's my ball, and then, okay, so it goes like that. That okay? We'll go do it. We're gonna have to go rent a truck. All right. Well, we can believe it or not. Whatever. Okay, it's not. We can argue that later. That's not an important point at this juncture of it. But do you agree that this distance would appear to be different than the distance from the person who just drops it? And so that's relativity. It all depends on where you are, you know, orientation to whatever it is you're looking at, right? Like I said, my computer's not moving relative to the center of the Earth. It is rotating, right? And then relative to the sun, we're moving, and then relative to the galaxy, we're, you know, right? And then, what's that? Yeah, I mean, yeah, exactly. I mean, there's so many things that, so, all right, let's get out of here. Let's go back to this. Functions of two variables. You need 3 dimensions to visualize. All right, so here we go. Here's your first example of a function of 2 variables. F of xy equals square root of x plus y plus 1 over x minus 3. Couple of things. Let's find f of 2, 1, f of 0, 0, f of negative 4, 1. Determine the domain, sketch the domain, and then determine the range of this function. It's a lot to do there. So let's write some stuff down. F of x, y is square root x plus y plus 1 over x minus 3. The first thing that I was looking for is for us to just evaluate part A. What is f of 2, 1? Now, when we say ordered pairs, right, ordered pairs, the order of this matters. So the 2 represents the x, the 1 represents the y. So you're not free to just choose which one you want to plug in for, right? So if I do that, I should get square root 2 plus 1 plus 1 over square root of 2 minus 3, which is, uh-oh. Oh, there's not a, what the hell? I don't know where that square root came from. I'm still in a truck, in the back of a truck somewhere. Do y'all agree with that? Negative 2? So if you plug in this ordered pair 2, 1, it spits out a single value, negative 2. Next one. What is f of 0, 0? On the top, square root of 1, bottom, negative 3. So you get negative 1/3. So it spits out this fraction, negative fraction. How about f of negative 4, 1? You get square root of negative 4 plus 1 plus 1 over negative 4 minus 3. Uh-oh. Square root of negative 2. It's not going to happen, right? So this is a non-real number, which means that, what? Can't do it, right? That means that negative 4, 1 is not in the domain. You're not allowed to plug this into the function. Just like we had in Cal 1, in college algebra, certain functions, you can't plug certain things into them, right? This ordered pair cannot be plugged in. In fact, would you agree that any ordered pair that had negative 4 as the x-coordinate wouldn't work? Right? Any ordered pair that had negative 4 would not work. No. Hold on, because your y could get big enough. I'm sorry. Yes. No, that you could. Negative 4 would not work unless this number was what? Bigger than 3, actually, right? Because you have a plus 1 out here already. Okay, but what about y's? We have some restrictions on y's also. Like, what if y was negative 10 and x was 1? It wouldn't work either, right? But that's not a good way of going about trying to figure out what the domain is, just by trying to guess numbers and different values. So part C is to determine the domain, like what works, what doesn't. I said part C, part D. So for the domain, let's talk about where we have problems, all right? What are some issues that we have with this function? Can't have a negative under the square root. So the first issue I have, the radicand, the thing under the square root, has to be greater than or equal to 0. Agreed? What's another issue I have? Can't have 0 in the denominator. So x minus 3 cannot be equal to 0. Those are my two issues, right, that I have to deal with here. The one on the right's pretty easy, right? X can't be equal to 3, period. No restriction on y here, just x can't be 3. So any ordered pair that we use, right, any one that we ever use, we can never let the x be 3. And then the other inequality, well, this is what we call a linear inequality, because it's a linear expression. And it's a linear inequality in 2 variables, which means that the solution set for this looks like what? Anyone remember how to solve linear inequality in 2 variables? If that was an equation, what would this be? If that was just equals, what would this be? Geometrically speaking, what is it? What is that a graph of? A line, right? The inequality makes you have to look at the line and shade one side of it. That's the way we do linear inequalities in 2 variables. So that's what I'll do. I'm going to solve it for y. Y greater than or equal to, move my x over, move my 1. Do you agree with that? And now, if it were an equation, what would it look like? If it were an equation, this is y equals mx plus b, right? So it would be a line, y-intercept would be negative 1. The slope of the line would be negative 1, so it would go down 1 to the right 1. Now, do I want to include the actual line itself? Yes, because it has the equal here. So you could be any point on that line would be okay. So I'm going to draw it as a solid line. What if I did not want to be on that line? I would do a dashed line. Now, the question is, which side of it do I shade? How do you figure it out? You can mess with this, but my recommendation, because sometimes this can throw you off, my recommendation is to just do what's called a test point. Just test something. Like, how about this point right here that we like, the origin? Does that point live in our solution set? Plug 0, 0 in to the original inequality and see if it's true. 0, 0 plus 1, is that greater than 0? Yes? That point worked, which means everything on that side of the line must work. So it would look like this. Shade it. With me? We're not done. Because I have to include this now into my final answer. So here's what my final answer is going to look like. My domain is going to be a picture. all right? It's going to be everything on this line. Wow, I screwed that up. Everything on this line. What could I not be, though? X could not be 3, positive 3. So that means that at X is positive 3, I actually have a dashed, I'm going to put a dashed line there to represent don't, like, pull all those points out. So it's everything over there except what's on that dashed line, right? Questions? No? So there's kind of two things I'd be looking for in a problem like this where I ask for a domain. I'd be asking for the algebraic representation of the domain, which would be this, along with this, and then the visual part of it, which would be the picture. You include both those, we're good. Is that? That's the answer, yep. Now, what about the range? What is the range of a function? The things that come out, right? The things that come out. I heard y values, but in this case, it's the z values, right? Because we have z is equal to f of xy, which is equal to the square root x plus y plus 1 all over x minus 3. The range is you might remember from college algebra, range is not always easy to find. Sometimes what we did is we tried to find an inverse function and then look at its domain, but let's just try and do it by visual inspection here. Is it possible to get positive numbers out of this thing? Is it going to spit out positive numbers? Well, the square root of anything is going to be a positive number, right? Yes? And down here, if I choose x to be bigger than 3, then I should get positive down there also, right? So I should get some positive numbers. Is it possible to get negative numbers? It looks like it. It looks like I'm only going to get positives out of this. If my x has got to be like maybe like 2 or 1 or something like that, I could get negatives here. So it looks like I could get some negatives. Could it ever be equal to 0? Could this ever be 0, the whole thing? Yeah, sure. You could make the numerator 0, couldn't you? So it looks like I'm getting some positives, some negatives. 0 looks like it's there. But that's not really a good way to say what the domain is. I mean, I can't say it's all real numbers right now because I don't know if it can achieve all real numbers. So we have to kind of wave our hands at that. The reason why I put it in here to determine range is because I want us to at least think about it. Like, you know, if this down here were squared, what could you tell me? It's always going to be positive, right? At least you can't have negative values come out. Okay, function of two variables. If we choose points in R2, we plug them into our function, and we get our outputs, right? As we plug more and more points in, we start to see the shape of what's happening. So here's three-dimensional space. I have a function I've already made up. You start taking these points, every one that you plug in, I'll draw on the board real quick. If this is like our x and y plane, xy plane on the ground, I pick some x value, I pick some y value, there's a point on the ground, right? That point, xy, gets plugged in, z value, it's either up or down, right? If I start doing that a bunch, as long as those points are in the implied domain, right, each one of those corresponds to some point, we start plugging them all in, more and more and more, and you start to get a picture of whatever it is. And in this case, it's a surface. You see it? Yeah, that's why it's slowed down. Yeah, if I bring it over here, it really does not like me. It's doing a lot of evaluations there. But then I can just fix the real surface right on top of it so you can see. Yeah, there. That's it right there. Okay? So functions of two variables give us surfaces. We've had surfaces before, but those surfaces we had did not have to be surfaces like this. They did not have to pass what we could consider to be the vertical line test again. Okay, if I take a line, imagine I come here and I take a line, I'm holding it parallel to the z-axis, all right? And I start punching holes through my surface. I should only hit the surface one time, right? That's what makes it a function. For every input on the ground, there's only one output coming up. So do you see why the sphere wouldn't work? The sphere? I punch through the top of the sphere, and it's going to come out the bottom, and so I hit it twice. So there's two outputs for a single input, so it doesn't work. But we still have surfaces. Let me back this thing down, because it'll hold up my CPU if I don't... All right, so the graph below illustrates the connection between domain and range. I was really, again, just trying to do more that I could to let people understand. So the domain is on the ground, right? So here's my domain. If I move this point along, you can see it, like which quadrant I'm in, and then how that gets mapped up to this point gets mapped up to the surface somewhere, right? So this f of x, y is the z value. It's the height of the function off the ground. Questions? Now, here's the graph that we just had a second ago, right? So I'm having the computer graph that function for me. And here it is. And let me rotate it so it matches. Can y'all see that function? Ignore all the speckled white dots. It's that piece of crap projector. I shouldn't say, it's probably going to burn out on me. We love you. Stay there. That's what that function looks like, all right? It's doing some weird stuff, right? If you look at it from like a side angle, it almost looks kind of like a rational function, right? Rational functions from college algebra did this like asymptotic thing, but instead of it just being a curve, it's actually like this entire sheet that goes up and down on both sides. Do y'all see that? What's cool about it, though, I think, is that if you look at it from straight down, what is that? That's our domain, isn't it? That's the domain graph that we just had. I'm looking straight down on the graph. Now, this right here is because I had an asymptote, didn't I? The graph is actually, it's diving down here, and then on this side, it's coming up. In this particular problem, it's asymptotic at x is 3. Now, I'll pull it off that. You see how... you see this up here? All those little like jaggedy edges? That's the computer basically going, shit, I don't know what to do, because it's becoming infinite. It's almost like if you have a graphing calculator and you've ever graphed a rational function that has an asymptote, it'll do this. It's supposed to be a line straight down. Have you ever graphed a rational function on a calculator and it does that? And so my college algebra students, they think that that's part of the function. That's the computer's inability to cope with the asymptote. So what it does is it goes, I'm trying to connect these dots together, right? And then this one's getting real big, and then it doesn't know what to do with the division by 0, and then it goes over here and says, wait, now I'm way down there, and says, what do I do about that gap? And it says, let me just connect it with a straight line. So that's what happens. Well, in this program, what it's doing is it's having a little trouble with the asymptote here, so it's just like making these jagged edges. Your graph doesn't really look that way. It's a nice clean sheet, just keeps on going up infinitely. All right, what about this one? Oh yeah, the range on that one, what it appears to be, I'm going to look at it from the side this way. It appears that our range is everything, because it looks like we get all positive values because of the asymptote. Looks like we get all the negative values because of the asymptote. And it looks like we do achieve 0, because we knew that we could make the numerator 0, remember? So it looks like we'll get every negative number, every positive number, and 0, so it looks like negative infinity to infinity would be our range. That would just tell you I know that this is asymptotic just because I know this goes to 0, while this just stays like a fixed number. Anytime you have a fixed number on top and the denominator gets really, really small, you're going to be headed to infinity or negative infinity regardless. Wait, say again? Uh-huh. Your function of x and y. Oh, yeah, that tells you what, yeah, that function is going to dictate what comes out, right? So, that's right. And you may not get everything. Just depends on the problem. So look at this one right here. Let's find f of 3, 2 first, and let's just do it visually. What would happen if I plugged 3, 2 in here? I plug in 3 here. Okay, I got a 3 here. What's 2 squared is 4 minus 3 is 1. Natural log of 1 is 0. So this is just 0. So when you plug in 3, 2, you get 0. Determine the domain. That's the interesting part. Determine the domain of f of x, y equals x times natural log y squared minus x. What's the only concern that I have? What can't be negative? Can't take log. The argument of the natural log has to be positive. It can't be 0 either. You're correct, it can't be negative, but it can't be 0 either. So we have to have, for domain, we have to have that the argument must be strictly greater than 0. Strictly greater. Otherwise I can't figure out the function's value. Log's not defined. Now this is an inequality again, right? But it is a quadratic inequality as opposed to a linear inequality. So we have to be a little careful with quadratic inequalities. What I'll do is I'll move the x over to the other side. And then next to it, let me rewrite it as an equal instead. Now let's just talk about this for a second. What is the graph of y squared equals x look like? Parabola to the side, opening up to the right, correct? Like this. That is y equals x squared. We want y squared to be greater than x, not equal. So we don't want this curve, do we? In our answer, we don't want that curve. So in the final answer I'm going to put here, I'm going to draw that curve, but I'm going to draw it dashed, meaning don't include it. And then to figure out which side of the parabola to shade. In other words, do I shade below? I'm turning sideways. Am I shading below or to the left? Or am I going to shade to the right or above? So again, we could just pick a test point and figure out if it works. Any point we want, as long as it doesn't live on the curve. So could I pick the origin? No, I can't pick the origin. So how about this? Negative 1, 0? Does negative 1, 0 satisfy this inequality? Right here. Or you could do it here. Doesn't matter. 0 is 0 greater than negative 1. Yes? So that point works, which means everything on that side works. So my domain should be everything over here. So on a test, quiz, or whatever, I would expect those two things to be part of your answer. Questions? Yeah? Did you say yeah? Good. All right. Here's that graph. This is a pretty cool looking graph. It almost looks like a plane, doesn't it? Almost looks like a plane, but there's some weird shit happening right here. And if I look at it from the top again, look at that. That's our domain. So as I get close to that parabola, right, it's like the Niagara Falls or something. It's just like everything's just dropping down, right? I like to visualize these because you can really see the domains when you graph them like this. All right, domain of this one. Don't worry, let's not worry about ranges, okay? We'll just talk domains. So what is the domain of the function f of x, y equals the square root of 9 minus x squared minus y squared? So what are you thinking here? You have a square root, right? So same thing as before, the radicand cannot be negative, right? So I know that for domain, I need that 9 minus x squared minus y squared to always be greater than or equal to 0. And any idea what the hell that looks like? What is that? Circle? Radius 3? That would be if it was an equation, which I agree with. Yes? If that were an equal sign, that would be circle radius 3. I move the variables to the other side. But basically what this says is you can have any circle you want as long as the radius is what? Less than 9. It's kind of like this. We know this is always positive, right? So this is greater than or equal to 0. So it's every circle with radius between 0 and 3. Did I say 9? I think I did say 9. Sorry. It's every circle with radius less than 3 or greater than 0. So it should just be what? What are we going to call that? Circle with radius between 0 and 3. So it's like a solid circle. We'll call it a disk. Is that okay? Like a disk? That's what the domain of it on the ground looks like. So anything inside here, radius 3, anything in there should work. Here's the graph. It's like a basketball. Just cut the top off, right? Or cut the bottom of the ball off. It's not solid. No, it's a surface. All right, but what's the domain? Look at it from the top. From the top, it's the disk. Radius 3. Make sense? The what? Yeah, don't worry about the range right now. I mean, on this one we could have said the range had to be what? Positive numbers, because square root always spits out a positive number. At the minimum, it could spit out 0, but that's right. You can't have the bottom half. In fact, if you look, if this is z, right? Z equals this. Square both sides, and you get z squared equals 9 minus x squared minus y squared. If you look at that, that's the equation of a sphere, but the whole sphere. See what I'm saying? All right, so I was talking about, the weather forecast and all that. What if you have a bunch of variables? Well, we can extend all these concepts, function of 3 variables instead. This time the domain, instead of ordered pairs, they're called ordered triples. The domain is 3-dimensional. The range is 1-dimensional. We need 4 dimensions to visualize. This isn't going to happen today. It's not happening. But we can still talk about the domain. If I have a function of 3 variables, right? Yeah. The domain is in 3-dimensional space instead of 2. So I could evaluate, I'm not going to. What's the domain of this? Well, we need the radicand to be what? Bigger than or equal to 0, right? So again, going back to the same concept, my radicand here is this instead of the other one. I just have the minus z squared instead, right? I need that bigger than or equal to 0. Move things over. What is this? X squared plus y squared plus z squared equals r squared is a sphere, right? That's a sphere, radius r, instead of a circle. And so our domain, remember, if we have a function of 3 variables, 3 going in, 1 coming out, our domain's in 3-dimensional space. We're saying that any sphere, any point that you pick can live on the sphere, has to live on a sphere, but the sphere has to be radius between 3 and 0, which is a ball, isn't it? So your domain is a ball with radius 3. You pick any point in that ball or on that ball surface, and you're allowed to plug it into the function. Do y'all see that or not? I mean, it's, no, it's sometimes a little difficult to visualize this. We all of a sudden went from 3. Now, that's going to be really important because we're going to need to be able to jump from different dimensions like that pretty quickly in our minds as this course progresses. All right. I would look at this again if I were asked about range, and I would say, hey, look, square root can only get positives out. I can get 0 if I just z. Yeah, are you saying t instead of z? Is that what you're saying? Okay. So yes, the output of this has to be positive or possibly 0. So, but the question would be, can you get everything out? Like, can you get the number 10 to come out of this? It won't come out. There's no way. Because the biggest this can ever be is 9, because you're always subtracting, right? Positive numbers. So the biggest that this could be would be 9, square root 9 is 3. So I can tell you right now that this thing, the range of it, is 0 to 3. That's it. What does it look like? It's actually a 4-dimensional ball, but you can't visualize it. It's 4-dimensional ball. We have these things in math called like unit balls, and in R1, in 1-dimensional space, the unit ball are all points that have a distance between 0 and 1 from the origin. So that would be, here's 1, here's -1. It would be this segment of the number line. That's what the unit ball is in R1. What's the unit ball in R2? All points distance 0 to 1 in 2-dimensional space. This disk. In 3-dimensional space, the unit ball is what? More like what we think, a ball, right? It's that solid ball, radius 1. But in R4, you have the unit ball also. It's just not, you can't visualize it. But it's all points that have a distance from between 0 and 1 from the origin to the point, but you can't see the origin. But distance is defined. In 4-dimensional space, distance is the square root of, just like we were doing with distances, like the Pythagorean identity, it's just an extension. In 4-dimensional space, you have that also. So you no longer need to visualize later as long as you have, well, like good definitions of what distances are and what order is, and it's beyond the scope of this class. We're done. Let's see, are we at the end of that? Yeah, what's the page number for that? It's 11.1 homework. 623. Now on those problems, do what they say. I say only don't worry so much about the range, okay? really focus on the domain and getting that established. If you go to Wolfram Alpha and you type in plot and then you put in the function of 2 variables, Wolfram Alpha will yield a 3-dimensional picture, but you won't be able to manipulate it. Like, you won't be able to do what I did and spin it around, but at least you'll be able to get some idea of what it looks like. Okay? Is that it? I feel like there's more. Do you have enough to finish your take-home? Do y'all want one more class on this? Y'all want this on Wednesday? We'll do it this way. If you turn it in Monday, I'll give you a little bonus. If not, it's due Wednesday. No penalty, all right? All right, I'll just give you a little more time. If you want any of your work that I've graded back, except for the quiz, I have it here. Feel free to come grab it. Yeah, I think that pop quiz is in there.